Hi everyone, I'm Wenhao Li from Shanghai Jiao University. The paper I'm going to present is called VButton, Practical Attestation of User-Driven Operations in Mobile Applications. This is a joint work with Northeastern University. So firstly, let's take a look at the user impersonation problem in reality, which commits various kinds of frauds. The first figure shows that there is a click farm in China that employs more than 10,000 real mobile devices to send fake user activities to earn repay or boost the popularity. And the second picture shows that many Twitter users found themselves follow some unknown Twitter accounts that they are not recognized. And the third picture shows that there's a bot network that simulates user activity to affect the political debates. So user impersonation occupies huge revenue in the internet. In general, the user impersonation could be characterized into two types. The first one is to do fake user activity on behalf of the real user. And the second is to mislead users to operate something that they are not intended to do. So it is very important, but really hard for service provider to verify whether a request from a mobile device is authentic. So we found that the root cause of these attacks is lacking of proofs to verify the authenticity of user-driven operations originated from mobile device. Consider a server receives a service request from a mobile device. The server needs to confirm that whether the operation is initiated by human instead of a bot or malware, and whether the operation meets the user intention instead of being misled. So there are many existing solutions trying to address this problem, but they are still enough. For example, reCAPTCHA. It requires a large user's involvement, and there are many anti-CAPTCHA techniques to make this approach less accurate. PIN and fingerprint authentication, on the other hand, is more accurate, but it is not lightweight because it requires users to authenticate every time they want to do some authentication. And besides, it is not intended to verify the user's intention. So we need an approach that could achieve both highly accurate and lightweight to solve this problem. So the purpose of VButton is to provide assurance to the service provider that an operation is initiated and intended by a human user instead of an unrecognized person. So from the application and developer's perspective, VButton is a class of customized UI widgets which has the remote verification capability. It ensures that the user does click the button and the user knows the semantic of the button. Technically, VButton leverages the ARM trust zone on the end devices to protect itself. So let's take a look at the overview of VButton. It consists of a VButton verifier and a VButton manager. The VButton manager runs in the secure world of trust zone and is responsible for on-device support. The VButton verifier, on the other hand, runs in the remote server and is responsible for service verification. For each secure operation, the verifier will firstly generate a VButton UI, which is a secure image for the manager to display. And in the client side of the manager will display the secure preview to the user using the secure UI in the trust zone for the user intention. And then it will provide some proofs on the user-generated operations by monitoring the hardware events in the trust zone. And technically, in the VButton, the display controller and the touchpad here are assigned exclusively to the trust zone to make sure that the VButton manager could exclusively and securely gather the hardware event to infer the user operations. So these proofs will then be sent to the remote server for further verification. So we provide two modes of VButton for different kinds of scenarios, namely explicit attestation and in-situ attestation. I will describe them later. So let's take a look at the explicit attestation. It is very useful when there are some scenarios when the semantic of an operation could not be expressed in a single UI element. Take a Twitter follow as an example here. When a user clicks the follow button, VButton will provide a secure preview of the operation in the trust zone containing the necessary information. Here, the information is who to follow here. For user to confirm, this information is securely displayed in the trust zone, and user could operate it securely to confirm it. And internally, how the explicit attestation works like this. When the user clicks the follow button, and the VButton will send the initial request to the remote server, and the remote server will generate a signed preview image. This preview image contains the necessary information that the user needs to understand for this operation. For example, it generates a preview saying that you are going to follow a Twitter, this account. And this image will then send back securely to the VButton manager in the client side and securely display to the user. And after the user reviews the preview and clicks OK, then the VButton manager in the background will receive the touch event directly from hardware and generate a signature of this operation and then send back to the verifier for further verification. The verification is done by using firstly checking that the request does send from the device and means the device key here, and then compare the preview hash with the original one generated in the verifier. So explicit attestation is very simple to use, but requires users an extra confirmation. In some cases, the semantics of an operation could be fully expressed in a single UI element. So let's again see the Twitter follow example. And in the right figure, the button in the right figure has enough information for the user to confirm his information. So this is, the scenario is very suitable for the in-situ attestation. So internally, let's see how in-situ attestation works. As before, when the user clicks the follow button, and the VButton manager in the background in the trust zone will capture the screen from of the button image, and then calculate the hash of the image, and then as the explicit attestation, this information will be signed and sent to the remote server for further verification. In-situ attestation poses several challenges. The first one is it's not like explicit attestation, which have a preview for user to confirm. The view in the in-situ attestation mode may update frequently. For example, the user may scroll the screen, and in that way, the position of the view may change. And it is very hard if we put the secure UI element in the secure world to coordinate with the normal world UI element. So instead, we try to solve this problem by render the in-situ UI directly in the untrusted OS and let the application to notify the VButton manager on any UI element update events. Note that if an application provides an inaccurate information to the VButton manager, the VButton verifier in the remote server will check and reject this request. Another challenge is since the view is rendered in the untrusted OS, how to ensure that the view integrity during the operation. For example, consider an attacker. He just changed the view just right before the attestation operation of the manager does. So in that way, the VButton manager may calculate an incorrect image of the view, which does not meet the user's requirement. We solve this problem by ensuring that the user has enough time to notice that the content that she operates and she's noticed, and then in the background at the same time, VButton manager keeps calculating the UI hash continuously to make sure the hash keeps consistent. So from the VButton application developer's perspective, we have designed a modularized SDK for application developer consisting of a client SDK and a verification server. And now this SDK has been integrated into a widely deployed TEE called T6. We have implemented VButton in both on different platforms, including the development board called Samsung Exynos, and also an off-the-shelf smartphone called Xiaomi Redmi. We have added less than 1,000 lines of code to the existing TEE, and the VButton manager is developer and deploy as an independent trusted application running in the TEE. It consists of about 500 lines of code. So in total, the TCP size added by VButton is less than 1,500 lines of code. VButton, since VButton heavily modifies the input event handling routine in different ways for each mode. In the original Android device, the input latency is 48 milliseconds, and in situ attestation mode, the touch event comes directly from the secure world to the VButton manager and then forwarded to the Android to consume. So the time cost is 52 milliseconds. For the explicit attestation, it's slightly different because during the explicit attestation, user needs to click twice. In the first click, that's to initiate the operation. The time consists of original Android input and round trip time going to the server to fetch the preview of the operation. And for the second confirm input click, because the click goes directly from the hardware to the VButton manager and is consumed by the manager itself. And the latency is very small, much smaller than the original Android input. So overall, the touch input handling latency is very small introduced by VButton. We also measure some other performance on the attestation latency. The first one is generating attestation blob and preview on both the client and the server are very computing intensive, and we measure the time cost as shown it in the left figure. We can see that it performs well when the size is very small, but if the application developer attesting a big image on the device, it is very costly. So we recommend application developer to avoid a testing image, such as capturing the whole screen for testing. We also measure the introduced performance in the attestation server. As shown in this figure, we have simulated 100 to 1,000 concurrent user requests using Apache Benchmark. From this figure, we could show that the attestation server scales well with very small service latency. So to conclude my talk, we have proposed VButton, which defends against the mobile impersonation problem using operation and display attestation. VButton enforces both the user initiation and user intention using the trust zone. It provides both the explicit attestation and in-situ attestation for different use cases. The VButton is implemented on different platforms with a very small modification. The TCB of the VButton is very small, and the design is very easy for application developer to adapt. So this is all for my talk. Thanks.